Welcome to the next topic in this second week, and I think today I want to go more into the notion of this thing called L1 identity. So L1 identity is basically a notion which allows you to compute the LP norms, L1, the total variation distance using something called an L1 norm of these functions. And let me give you the kind of basic introduction to this notion. So how this actually comes about. So basically, this is the L1 identity. So let's go into here L1 identity. So first of all, we define the notion of an L1 norm. So if we let f be any function from Zp to C, anything, it could be like having complex values or anything, and we define the L1 norm of f by this formula, so f double dash L1, and you basically just sum over the group of Zp of the absolute values. And that's all. So that's the notion of the L1 norm. And with the L1 identity, you can basically relate the total variation distance into these L1 norms. So the theorem, which is called L1 identity, is saying the following, that the total variation distance between two probability measures is given by half of the t from Zp of the mu t minus nu t. So that's the L1 identity. So this is for any mu and nu probability distributions in Zp. Okay, and this is an extremely useful identity because it does give you the kind of main ideas. Like it really allows you to compute total variation distance of various examples. So remember this example that I had in the earlier lecture. I have it actually above here. This d lambda delta 0 at Z3, and it took some while to go through all the subsets, and then we ended up to this answer. So before I prove this, I give you an example. So by the way, just to remind you that this was something I just noticed, that you need to have the of course the absolute value here in this example. So this is just given by the mu minus nu L1 norm. So that's the L1 identity. That's why it's called the L1 identity. If you use the notion of mu minus nu at the point t is defined to be just mu t minus nu t. Sorry about that. So let's give an example. So this example was this distance of lambda and delta 0 in Z3. So basically now we can just go through it. So by L1 identity, we have that this total variation distance, which would be difficult to compute. You just take a half of what you sum over the group Zt. So this is actually from 0 to 3, and what you have here, you have all these possible distances. So you have lambda t and then minus delta 0 of t. So what you can do is that you just go through all the examples that you have here. You see that actually it's only at 0 you have something different. So what you have here is that half of t at the point 0, this is equal to a third minus 1. So that's the first one. Actually, I need to use the absolute value. And then plus, lambda t at 2 is that's the 1/3. And then plus 1/3, because the distance it's at 0 at the Dirac mass is 0 at other points. So now if you just compute this example, this is 1/3 minus 1, which is minus 2/3, and absolute value is 2/3. So it's 2/3 plus 2/3, so you get half of 2/3 plus 2/3. So this is 2/3. So if you take the half out of this, as we claim. So that's all. You don't need to go through all the subsets. You apply the formula directly without any trouble. And so what I'll now give you is maybe another kind of expression. Well, I think I'll keep this for now like this. So for the end of the lecture, I will start the proof of this L1 identity. And I won't finish it until the end of the lecture. I'll stop it at one point, and then in the second lecture you can see the end of the proof. So if you want to watch only like the beginning, you can see the proof in this one, and then the rest of the argument in the other one. So let's start the proof of the L1 identity. So the proof of L1 identity. Okay, so what we have here is this notion of we basically, if the proof is in the lecture notes, and you can see that there are like basically 4 steps in the proof. So the idea here, so let's start with basically an idea of the proof, is to first it's like find a set, let's call it like B, that maximizes the maximum max mu A minus mu A in ZB. So remember that the total various distance is actually maximized by one of the elements because there's only finitely many subsets of ZP. So you need to just find one of those sets that maximizes this maximum. That's like the first thing to do. And then the second thing to do is that compute this mu B minus mu B to find it equals to this half T in ZP mu T minus mu T. So basically when you do the computation for this particular set B, you will end up to see that it is this maximum that you're hoping to get. So that's the kind of like main strategy of the proof. So what I'll do is that I start this proof by just giving you the construction of the set B, and then showing why does it maximizes the thing, and then the rest goes into the completing the proof. So let's. How would you find this set B first of all? So if you are now starting to do the proof, it's maybe a bit difficult to find out what might be the set B, and here it's not like that easy to maybe come up with the set without just maybe knowing already the proof. And here the basic idea here is that somehow when you look at like this picture, that let's say we have this previous lecture, we have this picture here. You would like to study the distance between two probability distributions. Here in this case, this was the lambda and delta 0. Then you could kind of like try to think that maybe if you want to find the distance, where did it come from really mostly? It seemed to come from like these kind of points where something is maybe a bit bigger. So this part when this is slightly more than that, and then these other points where it's like less than that. So there's you could maybe try to see that if you could take a set just the points where this delta 0, let's say, is bigger than lambda, so which is only this point, and then maybe using that set somehow to symmetricize the argument. So the set, from that kind of maybe heuristics, you can maybe try to think that maybe try this at least. So we define B to be equal to just the sets points in ZP such that mu T is at least nu T. So that's the set that we will consider. So it's just exactly taking the points where the other measure is bigger than the other one, and that's all. Like that's the points what we would have. So like in this example that we had in in the lecture notes in the previous lecture, if we had this this example where you had the lambda given by the probability distribution like this. We just take the points where and then this is delta 0. We just take these points where this is bigger than this. So for example, in the lambda t, if this mu would be lambda t, we would just take these 2 points. That would be the set b in the points where this would be bigger than. So we ignore the other points. And then we just basically want to compute this distance over these 2 points. And now the first thing to do is to create this kind of like a formula for the thing. So what we want to do is the maximization. So the step 1 is to prove this kind of a formula. There's kind of like a symmetric notion of this. So if you take this distance between these 2 measures, mu b and nu b, then this is equal to nu b and its complement. So you change the order here, you take its complement, and then mu b and its complement. So here, what we have here is this complement in this set, and we have this kind of symmetricity going on. So the proof of this, let's prove this first. How would we prove this, that this is equal to the thing? So so by definition of b, we have that the measure of b is at least the new measure of b. That's because the definition in this set, all the values of mu t is bigger than nu t in this definition. And so if you have this property, this implies that if you take the absolute value of mu b minus nu b, this is just equal to the same as mu b minus nu b, because it's non-negative. And then if you now use if you remember from the previous lectures when we talk about this probability distribution, defining this notion of a measure, it has this additivity property. So if you have 2 disjoint sets, for example, and taking their union, then the union has the measure given by the sum of their elements. So thus, by additivity, we obtain the following, that if you take this mu b minus nu b, and then you subtract the one that we want it to be, so mu b complement minus mu b complement. So remember, this is what we want the expression to be. And then we just reorder these terms. So let's reorder them that we have the same. So you can see that this is the mu b and mu b complement, and then here we have the nu b and nu b complements. Let's put them on the same thing. So we have mu b and then plus the complement mu b complement, and then here you have the other side. So you have minus nu b plus nu b complement. That's how this came into be. So we have this one and that one, and then here this green one. Okay, and now we can see the additivity. So this is the additivity. Because these are disjoint, then of course this is just equal to the measure of the zp, and then you have minus mu of the nu of zp. So, but these are both equal to 1 because these are probability distributions. So then this is just equal to 0. So now you have seen that this step 1, this claim is equality arises from here, because this is equal to 0. So that's kind of like the first step of the argument. And then in the second step, what we will have is that we want to then see that this B maximizes the entropy. But let's leave this for now, like just to this step, and I will show you the the rest in the second lecture. So why this formula that we just proved will be very important to obtaining the claim. So we had this like very simple expression, this symmetricity condition, but then we will use that in a second to prove the claim.